Okay, I think most people are back, so welcome back. We have a slight shift towards the more methodological in this session. So we had a really wonderful introduction about some of the main challenges and also some of the promise in the morning's session. So I'd like to introduce our four panelists. And I'll just start in the order that they're sitting. So Chandra doesn't need much of an introduction. You heard from him this morning. He's the director of CTR here and a professor in civil engineering. Joydeep, he's a professor in electrical engineering, as am I. So we're direct colleagues. And Joydeep has been working in data mining for quite some time in various applications, but has recently started focusing on questions in transportation. Next we have Xiaoqing Zhu. And I'm extremely pleased that she's here. Xiaoqing got her PhD at Stanford and has been working at some time for Cisco, and now is a technical leader for Cisco here in Austin. And she's worked on numerous areas, wireless, networking, video, and has recently been interested in how all of these interact with big data, data analytics. And so it's great to have her here and to hear her perspective. And then last at the table is Doug Fearing. Doug is a professor at McCombs and has worked on various aspects of data mining in the air transportation sector. And so it will be great to hear from you, Doug, as well. So I think we'll just start in this order, and then after our panelists finish, I'll have some general questions to ask them. Thank you.
Thank you, Constantine. So let's, what I want to talk about, and I know I have about 10 minutes, so I'll try not to go into too much of the methodological details, but give a flavor of how some of the analysis techniques that my students and I are focusing on and developing might be brought to bear for important considerations of translating these voluminous amounts of data into valuable information. And again, the issue is one of timing. You want to try to do it in a reasonable amount of time. So by way of introduction, there is a growing interest in the joint modeling of data with mixed types of dependent variables. And I'll give you examples in our transportation context in just a minute. But when I say mixed types of dependent variables, we're talking about some variables that may be continuous, such as speed, some variables that may be binary, such as whether a vehicle is in the outermost lane or the innermost lane. Some variables that may be count variables, such as the number of autos that a household might own. So you have this mix of various dependent variables. Now there's a lot of interest because we're getting these huge amounts of data over time and also over space. And in clinical biology, for example, the whole issue of what's the effectiveness of depression medication in reducing occurrence, which is a binary variable, frequency, which is a count variable, and the intensity, which can be a continuous variable. It's a huge issue because we are able to get data at a very, very fine level of temporal resolution today and from many people. The same in health. The same issues are also here. And in transportation, we talked about this, translating voluminous amounts of data in near real time. But it need not be in near real time. It could also be for planning purposes to take some proactive actions. So there's this field of data science that has been there for some time, but is really coming to, if you will, to the fore these days. Not enough humans to process the amounts of data that we receive. Okay? And so we have had machine learning, and Joydeep Ghosh will certainly talk much more about visualization, advanced computation techniques. But there's also the statistics, the social sciences, and the domain knowledge that also needs to be brought to bear. And how do we marry these techniques? They're not necessarily mutually exclusive, though in many ways it seems like computer scientists have gone off and done their thing, and some of the domain experts have been focusing on statistics and social sciences. Once again, not that they are mutually exclusive, but the whole idea of bringing all of these things together into a field of data science. So the question is, why are we interested in trying to extract information, joint modeling or whatever, borrows information on other outcomes? Now, this could be in the context of other variables, dependent variables we want to predict, or it could be in the context of a whole large set of independent variables. The idea of being able to integrate data to increase accuracy as well as precision of information extraction. The more the information we receive from multiple sources, it can not only allow us to increase accuracy certainly, but also the precision of the information extraction. And this is something that is being hotly debated in the field that I work in, but in other fields too. Some of these techniques can help distinguish between causal effects and associative effects. Now, there's a school of thought that asks the question, why do I care whether it's causal or whether it's associative? You know, if I know that a certain mix of variables would lead to a certain kind of outcome, why do I care whether it's causal or whether it's associative? Now, I would argue that there is a reason to be distinguishing, if not in some operations-related applications, in planning-related applications. And I'll come to that in just a bit. So one of the problems all of these methods tend to face is the voluminous amounts of data, the huge amount of dependent variables that we are focusing on perhaps, or the huge amount of independent variables. And there are many methods that have been proposed in the past. And one of the methods that we developed, I have a book on what I'm calling composite marginal likelihood, is that deals with high dimensional independent variables which I think would be appropriate for transportation operations, or high dimensional dependent variables which may be appropriate for planning. And again, just bear with me, I'll come to that. So let's move to connected vehicles technology and the high dimensional data we are talking about. Vehicles, you know, with all of these connections, you know, they have embedded receivers, they have wireless network interfaces, cameras, all kinds of things. They also have to interact with roadside sensors, and unlike what has been done in the past, where you have data being sent to a central repository, processing over there, today the whole idea is to try to see if we can process things locally and thereby increase or decrease the latency, if you will, of decisions, so that we are able to make decisions in near real time. Okay, so this just once again trying to show you the vast amounts of data that's really needed by these sensors to keep vehicles safe on the roadway. So basically you have a huge number of variables. Now, let's keep it simple. I'm going to give an example from the operation side. Assume two vehicles and an isolated non-signalized intersection. Keep it simple. And assume that all measurements are captured precisely. So we exactly know the deceleration ability of vehicle given a vehicle type. So all of those are recorded with precision. Even in this context, what we have is, you know, if you're talking about trying to see if there's going to be a crash or not, as we see things now, we need the speed of the vehicle 1, speed of vehicle 2, and those could be continuous variables. You also need accelerations of those vehicles, which I'm not showing. Obviously, we need to have information on the position of the vehicles, the direction and angle of progress, you know, the vehicle type, age. These might help in terms of translating into capability to decelerate, and of course, weather conditions. And these are groups of variables. Within each, you have just, once again, a host of different variables. Now, these are what I would characterize in an operations context as independent variables, right? Now, you could have thousands of these independent variables, right? There are methods that can be used in this kind of a setting with lots of independent variables. We call it multi-index discrete choice analysis. And the idea is, can we translate all of these independent variables into a much fewer set of indices, which one could characterize as, we're not seeing it, but essentially capture the information of all of these independent variables. And so once we have those, then the crash, whether it will occur or not, can be determined much, much faster. Now, of course, I was simplifying things. We need to know the position and trajectories of other vehicles. We need to, the human is there in the loop. Even with connected vehicles, that's going to be there. The age of the person, and with all of these stochastic elements, the model that I presented earlier of crash occurrence is actually becoming now a probability. What's the probability that a crash will occur at time t plus 1, given we are at time t? Okay, so it becomes a probability model. And the ways we can do it, similar to what I showed on the previous slide, you could have a projection where you reduce the number of independent variables to much fewer, and then you estimate a model in a subsequent step. Now, one of the things I want to emphasize here is in this kind of model where we have many independent variables, the arrows toward these indices are inward. So they go inward, so you're collapsing this huge set of variables into much fewer indices. Okay? Now, the same kinds of things happen for all of these other potential applications too. Now, let's move to the other side. Lydia, who's not here, was talking about planning, right? Now, in planning, assume no connected vehicles, and let's look at what we do today. Consider residential choice and activity travel behavior, right? And what we have is, one could argue that the choice of dwelling, how many bedrooms we want, how many bathrooms we want, what's the lot size, all of these dwelling unit attributes are decided along with where we want to reside. So the residential location is a package now along with other dwelling unit attributes. Now, in this particular case, there's an example of many, many dependent variables characterizing dwelling unit attributes, but also location attributes. How do we model this kind of a setting? The one way to do it, and this is where I was referring to some of our earlier work, is to construct latent psychological constructs, which we believe will impact all of these choices. So green lifestyle propensity. Okay? If a person is green, the person might decide to have a small lot size, might decide to live in the city, might decide to have an apartment, might decide to own fewer vehicles, right? So all of these things could be attributed to green lifestyle propensity. You could also have a luxury lifestyle propensity, which is in some ways the other side of the coin, but not quite. And how do we manage this in the framework that I was talking about earlier? Here, all of these are dependent variables. We are interested in how people make these choices because they are all joined. Okay? So unlike the example I gave earlier on the operation side where we had a huge number of independent variables, here we have a huge number of dependent variables. And the idea is that while you have demographic factors that impact all of these dependent variables, there are some latent stochastic psychological constructs that essentially give the jointness. And why is this important? The reason why this could be important is consider building high density neighborhoods with the idea that with a higher density neighborhood, you're going to have people owning fewer vehicles, right? Now, if the question is from data, can you make out that causal relationship? Okay? Can you say that density of neighborhood actually impacts the number of vehicles? That's a huge question in land use transportation modeling. Why is that a huge question? Now, if it is true that, you know what, people who are green will decide to live in high density neighborhoods and also decide to own fewer vehicles or more compact vehicles, then it might not be that the fact that you have high density neighborhoods is what is causing fewer vehicles. It might just be people who are green choose to select this as well as select fewer vehicles, right? And that's important to distinguish. That's where the associative versus the causal connection needs to be very, very clear. And by having this kind of a setup where we have some unobserved stochastic variables affecting these variables, but all of them too, and then after that having an additional effect of density on household vehicle type size, the idea is you can isolate the causal and the associative effects. Okay. I know I'm running out of time, but 2 more minutes. Okay. So far I was talking about planning in the large context of no connected vehicles. Now let's introduce connected vehicles, right? I'll skip over, there's been a lot of discussion, and appropriately so, about the safety enhancements, the potential capacity enhancements, the energy and environmental benefits. And what we try to look at is, yes, but what are all the possible unintended consequences? Let's look at also them too. And so, people might live and work farther away. I mean, travel time, I can sit in the comfort of my vehicle, I'm not driving. Well, I'm going to live in the boonies. Why do I care about where I live, right? Now, that could increase commute distance. Okay, that's a possibility. People might want to access more desirable and higher paying jobs, and so be willing to commute more. In general, on a daily basis, once again, time does not matter. I might visit destinations farther away, and this could lead to sprawl cities. And these are the kinds of projections and possible consequences. Now, the intent is to look at what could happen because of how humans might behave and try to take some proactive action. So perhaps appropriate zoning regulations are needed over here. But we could try to stem some of these potential negative impacts. The same with household vehicle fleets, right? I mean, I'm living in my vehicle for quite some time because I'm not driving. So I might actually start having a recreational vehicle. I remember talking about this with Joydeep in an earlier presentation. I mean, Joydeep might want this recreational vehicle. I mean, I'm spending most of my time here. At the extreme, this is just an extreme. Think about this. We don't have homes anymore. We live in these vehicles. Okay? Those are our residences. Okay? Now, the same with impacts on mode choice, and I won't belabor some of these things, but the essential issue is time might be less of a consideration. Cost might be the main policy tool to influence behavior. Okay? That is something we have to be cognizant of. Now, how does all this play in our framework? Now, just like what we had earlier, we might have green lifestyle, but now also have multitasking inclination, tech-savvy people or geeks, so-called. So these are now the latent variables, and essentially then what happens is, if we go back to this flow diagram, now we have more of these propensity variables, and unlike what I showed for the operations case, these arrows are going outward. So these are all being determined by some of these fewer number of latent psychological constructs. So it's another way of reducing the dimensionality of the problem. Okay. Let me see. I think I just had one more slide, but so the bottom line: data to information. It's an important data science. Stochasticity and uncertainty is a big part of this, but I would argue that more uncertainty implies more need for planning. Okay? The example I like to give is, if you know a city very well, you're not going to be doing any planning. You know it very well. If you go to a city to visit, that's when you're going to be doing much more planning because you're much more uncertain about the situation. The same thing over here too. And so analysis and planning must recognize the uncertainty, and that might, engender the change in some of our current ways of thinking and philosophy. So let me end there. And Constantine, I hope I was okay on that.
Great, thanks very much. So, Joydeep is the next one. Yes. So we'll have a chance to pursue some of these topics.
Constantine.
In a few minutes.
Thanks, Chandra. So I'm actually very new to this community, so I'll start with a word on my background. And Chandra's also already talked about why I'm now interested in transportation, because I want to get one of those fancy over-the-top okay? So about 20 years back, I founded a research group at UT based on trying to understand data-driven reasoning and insights. What would be nowadays called big data analytics or predictive modeling. And over the years, we looked at a whole bunch of complex engineering problems, and we looked at signals, videos, images, transactional data, streaming data, and web data, and so on. And one of the things we've learned over the years is that if you have very complementary sources of information, it's good to use that. And for each of these, there are different communities who have tools. You have the AI machine learning folks, you have the pattern recognition folks, stats, and so on. And what you really want to do is to pick and choose, and more importantly, combine multiple tools in a principled way so that you can come up with very robust and well-performing solutions. Okay, so so what I wanted to give is a very broad sweep of this area, broken into last century and this century. Okay, so if I look at what people did in the last, say, in the 80s and 90s, in most of the work which you talk about, large-scale heterogeneous data and information processing, would come under the moniker of multi-sensor fusion, and much of this work was funded by DoD. Okay, so you might think of a smart ocean surveillance system, and you'll have sensors of all types. You have from satellites to buoys under the water. These are slightly different from transportation systems in the sense what you're trying to track are much more complicated. So you have airplanes flying or getting into dogfights, and they're not going to follow a particular road, right? So they're totally off-road vehicles. Okay. On the other hand, the number of objects you're probably trying to keep track of is much, much less than what you would look at in a big urban setting. So in some sense, these are much more difficult. In some sense, they're much easier. If you look at the kind of reasoning that is done and the different levels it is done in, these are probably things you will relate to much more. So you might be looking at some very low-level things like just detection of various objects, trying to understand what they are, how to track them over time. If you have multiple objects, how you keep track of all of them. And then more at a higher level, you're looking at, what is the intention of these objects, and so on. So if you forget about the threat part and calling the object as a target, but instead you just think about these as vehicles, and instead of a threat, these might be collision avoidance, this is something that should relate very, very well. And actually, this is pretty much following the pyramid that Dr. Walton talked about, where you have data, knowledge, information, and wisdom. Okay, and many good techniques have been developed in the 80s and 90s for these different layers, and basically go from very basic detection, estimation, tracking theory to things like blackboards, which are an AI technique for knowledge-based systems. So there you need to bring in a lot of context and domain knowledge into bear, and have a systematic place where you can, all the reporting is done and all the actions are transmitted from. So when I was looking at refreshing myself on the rationale for these systems, I came across this quote, and I said, well, this could also apply to a very transportation setting. And let me try to read this out. Essentially what they're saying is, we are looking at situations where there's high decision risk, and where essentially what you're trying to do is to compensate for human restrictions. You could be distracted, you can have too many things you might that are competing for your attention. You might have a combinatorial set of choices which is difficult for humans to process, and so on. And I would agree, this is actually taken from a review which was a survey of DoD-based defense systems, but I think this would apply very much to modern transportation systems as well. Okay, so if you look at an overall architecture of systems at that time, there's way too much detail. The only thing I wanted to point out here is that you have everything from domain knowledge and human intelligence to multiple sensors, and all these arrows are bidirectional. Okay, so many of the interesting ideas in that era were how do you adaptively sense based on your needs? So with minimal amount of, so these are really not passive sensors, but active the least amount of information that will sharpen your hypotheses the most. So those are the kind of ideas that have come out. And the two very extreme and simplified design choices that people would make, if you have multiple sensors of multiple types, is A, you could have some intelligence built on each sensor and process the information from each sensor separately. And then you fuse all the answers, so that's more of a decision fusion. Versus first you put all the data together, so that will be a data fusion, and then you build your predictive models. Okay, so those, and there are of course many hybrid situations that fall in between. But these are, I would say, the two extreme design choices that you need to make. And I'll just highlight some of the work we have done on the first design choice, which is just to keep matters simple. So about 20 years back, so we teamed with a company called Tracor that used to exist of MLK. It was a defense company, and we basically found there was a big DARPA challenge which we won, and essentially the idea was to track things happening in the water based on various types of sonar sensors. And essentially what we found is that you can process these sensors many different ways. You can extract many different representatives of the data, and all these representatives have some complementary information. You can build different types of classifiers or predictive models, right? And then what we really did was to bring up with a theory of how we combine the answers from these multiple statistical models, which might have different reliability, different areas of expertise, and so on. And nowadays, these techniques are now very bread and butter. You will find them any standard statistical package. We also looked at combining multiple clustering solutions. So clustering, they're grouping all the objects that you're seeing into homogeneous groups. And this turns out to be much more difficult because different ways of looking at the data might give you different numbers of clusters. And also what I call group A may not be your group A, right? Because there's no predefined semantics to what A means. It's just the first group, right? So we developed a theory of how to combine multiple clustering solutions as well. And then the final one, this I had to dig out from an old paper, so now it really looks very dated because it is all fading and so on. The lines are not solid. But essentially what we did is we were faced with a tracking problem. It was actually an aerospace application. So I did this with Bob Bishop, so your colleague. So the idea is, so the standard technique is to use a Kalman filter. But in the Kalman filter, you have to assume certain model characteristics, for example, how the noise matrix looks like. And you may not know that in advance. So what you do is you actually use a bunch of Kalman filters. Maybe I'll use mine this way for a change. You have a bank of Kalman filters, each with different assumptions. And then you have what's called a gating network that mixes the answers with different weights of the different filters, right? And the filter that is better performing gets more importance. And then the dynamics of what you're trying to track changes. For example, a rocket fires a booster stage, then it very quickly switches to a different filter. And all this is done automatically. It's all data driven. And actually, we outperformed the McGill filter bank, which was being used at NASA at that time. So that's my 20th century summary. And now we come to the 21st century. So instead of having these faded drawings, we actually start having color. Now, Chandra actually showed a 2015 version of this slide, which had much more fancy 3D graphics. But this is, I'm just getting there, okay? So in the modern setting, some of the heterogeneous data situations, of course, would be transportation. There are other situations. In fact, if I was thinking about what's the main difference in the type of data between 20 years back and now. And I think much of the large-scale data we saw are just inherently networked data. Okay, and that's the big difference. And the networks are huge. So, for example, if you think about the Facebook network, the nodes are actually just not people. They could be companies, organizations, and so on. And the relations can be of various different types. So there's heterogeneity in the relations, in the nodes, in the properties of the nodes, and so on. So there's heterogeneity everywhere. And of course, you'll be sometimes aghast by the kind of ads that Facebook gives you, they can, or LinkedIn, they are very good at analyzing these very large-scale information networks. I have 3 minutes. I can talk about one method since I wanted to talk about one method. So one of the new ways of trying to analyze this kind of data is using what's called matrix factorization technique. So to give you a toy example, so suppose I have a matrix of, I have a whole collection of text documents. So each document you can think as a distribution of words, or what are the words in the document. So I can think of my entire data as a document by word matrix. Okay. Now what you can do is you can try to approximate this huge matrix by a tall narrow matrix and a short wide matrix. Suppose this matrix has only 3 columns. Then each document, instead of being characterized by so many words, you're just characterizing by 3 things, which are these 3 numbers. And essentially these 3, and now these are also distributions of a word, so you can think of these as topics. And essentially what you're saying is a document is represented as a mixture, which are these are the 3 mixing coefficients of the 3 topics. Okay? So you're positing that there are a small number of topics, and each document is a convex combination of these topics. And this is a much more succinct representation, and it has lots of uses, from understandability to succinctness to actually noise removal and so on. Okay, because this is an approximation. Quite often the original matrix is very noisy, and you try to extract the essence of this matrix. Okay. Now this looks like homogeneous data. It's all text, but you could have another matrix. For example, you can talk about documents and people who look at those documents. So you have document versus users. You can have a social network among the users. So you can think of many such matrices. Okay. Now, if you want to fuse these two different types of data, the document user and the document text, you could posit that perhaps the latent representation of the documents will be shared across these 2 matrices. And there are techniques for doing that, those things like collective matrix factorization. And this is the way you are going to pull in multiple data types. Okay? So here's a much more complicated situation. So here, this is some work we did last year. We are looking at electronic health data. And so I can think about patients versus medications versus diagnoses. So now instead of a matrix, I have a tensor. And again, I can factorize it into several components. And if these components are very sparse, what you're doing is you have a whole huge amount of patient data. This is hundreds of millions of elements. This is from an electronic medical record. But you're representing that as a sum of some very sparse components. And these sparse components are very easy to understand. It's basically a small combination of medications and diagnoses that represent an important disease. So this is what's called a phenotype. So this way, you can extract phenotype from large-scale data. So again, you're talking about knowledge from data. Okay. Now you can think about this in a heterogeneous, even larger scale. So here's another example from recommender systems. But let me come back to the medical example. So now instead of just the patient diagnosis procedure matrix, I can think of many other matrices. You have a referral network among the doctors, which actually can be used to analyze fraud, among other things. Okay? But you can think of, you have many different types of matrices and tensors that represent health data. And how do you jointly analyze all of these? Okay? So I gave you one example of more modern data and one example of a way to try to analyze such complex heterogeneous high dimension data. Okay? And of course there are lots of other areas where this is just blossoming, and I think we'll have fun for the foreseeable future. Okay? Thank you.
I can just press the page down, flip back.
Yeah, but I think this.
Hi, it's a great pleasure to be here, and I've heard already many nice talks from the academia about the tools for addressing the upcoming connected vehicle and intelligent transportation, and also the support from the government and public sectors in embracing this new feature. So I thought maybe I can throw in something in the middle that, I mean, honestly, from the private sector, at least my understanding from Cisco is that we don't really have a solution yet, but we're very much interested in adopting the great tools to the problems that we're looking around and exploring and really trying to bridge the gap. And it's also great to be the next speaker right after Joy did, because he has already laid the stage for showing that it's important, and there are great, sort of data science tools you can use to fuse information from heterogeneous data and sensor data. So here I'm just trying to throw into yet another rich mode of sensor, which is kind of the ultimate mode of sensing based on visual information from video sensing. We're really considering high definition camera input as yet another mode of sensor. So with that, also I guess for this group, we're not really need to be, we're already in consensus regarding the upcoming explosion of connected devices on the planet, and we're really trying to, get prepared for it so we can basically skip. The idea is that the connected devices will really bring the interconnection of objects as well as the network operation into yet another new mode. So as I mentioned earlier, we're really very much interested in integrating different types of sensor input into the network platform and ultimately feed them up to maybe deep more sophisticated offline learning in gaining insights that are not immediately human recognizable. So personally, since I come from more of a video research background, I feel that video can be a very special type of sensor in the sense that it can be probably a very versatile type. You don't collect specific mode of information. Instead, from HD video, it is possible using computer vision techniques to derive different types of metadata out of the same video input. For instance, here on the bottom graph, I'm showing the optical flow information, which basically derives the motion information out of the field of view captured by the camera. And in addition, although we're all very much familiar with HD video that we use on our smartphones every day, there are other types of video that, especially in industry, which basically are capturing sort of not visual information, but thermal information or even high spectral sort of measurements. So they're really measurements captured as imaging, and potentially you can sort of capture high frame rates sort of measurement data over time. So we really think that by considering video as a sensing mode and also considering different modalities of image capturing or video capturing, we can open up the door of, sort of to a much wider reach of information input. So with that in mind, the key challenges, technical challenges we consider in sort of embracing video sensing into the IoT platform would be first and foremost, of course, is the high bandwidth demand from video sort of input, especially when you have a dense camera deployment. Especially given that many of the cameras themselves can be wireless, and typically the upload bandwidth from a local site to a remote, for instance, a cloud server, can be still fairly expensive these days. And secondly, many of the speakers in this talk, in this morning, has already pointed to the need of low latency decision making, driven by the sort of data and input information, so that tight latency requirements is kind of a requirement for some of the event detection and reaction use cases. For instance, in vehicles, maybe in collision detection, etc. But on the other hand, it becomes now maybe not even feasible to do the sort of the data mining up in the cloud and then feedback decision back to the local sort of operation sites. together with that, if we want to carry out much of the learning locally at the site, then many of the computer vision tasks can be computationally expensive to carry out locally. So that's the type of technical trade-off that we would want to sort of stride out correctly for different usages. And finally, video information naturally brings up concerns regarding security or privacy. And when we deploy them sort of more widely, you don't really want to be watched all the time. It's, maybe for a familiar audience, a friendly audience, but you may not really want your face to be uploaded to the cloud all the time. So these are the main, technical challenges we have identified for enabling video sensing, in the IoT platform. And our approach, we think that a good solution, sort of the way to sketch out the solution is probably to allow an intelligent, to allow an intelligent middle-tier architecture between the endpoints and the cloud data centers, in the sense that at least that's where we could host some of the partial or initial sort of computation by extracting out the essence from raw data and only uploading the sort of the features instead of the original data. That can be a good way to both address privacy or security concerns, because the data you have parsed out of the analysis of the raw video becomes much less recognizable, and at the same time, that's a way to filter out the at least 90% or sort of a majority percent of the raw data to make it feasible given the bandwidth requirements. So with that in mind, the type of architecture solution that we have sketched out is really to leverage the fog servers that's being present there between the endpoints, the data sources, and the cloud-hosted data center. So the analogy we use is really coming from, Cisco is based in sort of Bay Area, San Francisco. It's really the fog that is kind of, can be permeated over a much wider presence, and that bridges between really the clouds up there and all the endpoints on the ground. So basically, it can facilitate data moving upstream, and in the same time, add in some of the processing and in between. And at the same time, because it hosts local computation, it is also possible to accommodate sort of simpler, higher level code that are application-driven, getting them deployed onto the fog platform servers. So this is really a sort of a complementary analogy that we think, at least on high level, and can be the architecture that we leverage to accommodate high-density data analysis, including video sensing, in the IoT platform. So that's really kind of the sketch of the solution here. We think that from Cisco's point of view, we're interested in a broad set of applications. So they're all here, but the main ones that we're focusing on, transportation and connected vehicle, is definitely one of them. And industrial automation is another one where we think, given the connectivity sort of all the endpoints and devices, as well as the emerging trend of converging the underlying connectivity network to Ethernet-based, sort of more standardized-based, there is an opportunity to revamp, relatively speaking, old industry. And finally, we think that this is also a great opportunity to leverage this technology with a more sort of a social impact in, sort of urban planning and smart, sort of leveraging them in urban planning and smart cities type of, use cases. That's really what I have, and I think this is probably just a sketch of where we want to go, both in terms of technology and also in terms of finding great opportunities, for business. And I would love to basically maybe get questions, and we can, strike up more discussions during the panel. Thanks a lot. Thank you very much.
And our final speaker, before we switch to some questions that I have for our panelists, is Doug Fearing.
Okay, so I'm going to talk about a couple of applications from my research. I am a professor at UT Austin McCombs in operations management, and I focused a lot of my research on air transportation. And so one of the challenges in air transportation, especially data-driven research, is that a lot of the information that is publicly available is aggregated. So aggregated flight information, aggregated passenger information. And when you think about trying to analyze, again in a data-driven setting, how to deal with passenger or crew, we lose that heterogeneity. So I'm going to talk about two applications and how we try to recover that using simulation. The first project is a project actually from my thesis, working with Cindy Barnhart, Vikrant Vaze. And basically here we wanted to try to understand passenger delays. So from the perspective of a regulator, you're much more interested in passenger performance of the system than you are in flights, right? Because flights, again, in an aggregate basis, hide a lot of the variability. I mean, even if you think about flight size or aircraft size, you can go from very small aircrafts, 100 seats, to 747s with 250 seats, right? So trying to understand how the system performs from a passenger perspective is particularly important. So we built our work off of an earlier paper which looked at a small set of data to show that, that these passenger delays, in addition to thinking about these flight delays, obviously depend on misconnections and cancellations. So we need to incorporate that level of granularity. And US passengers, the cost in terms of time lost is billions of dollars per year. Obviously, this is an important question for the US transportation system, National Air Transportation System. And so there have been multiple methodologies for looking at this. The Joint Economic Committee estimated about $7.4 billion in passenger delay costs. And there they ignored flight cancellations and passenger connections. So again, just looking at flight delays. Or people have looked at this from a simulation perspective. If we try to simulate passenger connections and therefore break down delays around 8.5 billion. So just to give you a sense of the data sources that exist in air transportation context, I talked about we have flight data. So that's one of the nice things about working in air transportation is we have planned and realized flight schedules for all of the major domestic carriers through the Flight On-Time Performance database that's maintained by the Bureau of Transportation Statistics. We can get flight seating capacities. We have actually the registry of aircraft for each of the carriers. So from that, the inventory, so we can get their codes, their tail numbers, on a monthly basis, how many seats are available. And we do get some aggregated passenger demand. And so this is the big part of what we've looked at is how we take this aggregated passenger demand, either monthly segment demand. So what I mean by that is if you think about US Airways has a segment from Phoenix to Austin. Right? On a monthly basis, we can figure out on that flight segment, that leg, how many passengers traveled. But we don't know which of those passengers were on non-stop itineraries or one-stop itineraries, multi-stop itineraries. Now, that is layered with a sample of itinerary data. So the DB1B ticketing database maintains a 10% sample of passenger itineraries. So here we're starting to be able to take this aggregated data and at least get some idea of how this is split up across various itineraries. And so what we really are relying on here is the fact that we can use the heterogeneous booking data. So we receive data from proprietary booking data from a single carrier for a quarter of operations. And we use that to try to understand from those aggregated data sources how can we recover the heterogeneity of passengers. So methodologically here, what we're doing is we developed a multinomial logit. I have in parentheses discrete choice-like model of itinerary shares. So taking those, that aggregated data, again, the segment data and the itinerary data on a monthly basis, and using our proprietary data from a single airline to regress the distribution of passengers based on factors like time of day. Obviously, we see in air transportation that there are big peaks in passenger demand in the morning and in the evening. Looking at day of week, connection time. One of the interesting things about connection time is, as you would expect, passengers tend to prefer a connection time of about an hour. So there is disutility associated with shorter and longer connections, right? So longer connections because of the time aspect, and the shorter connections because of the risk of a misconnection. Cancellations, this is what actually makes it not quite a discrete choice model. So what we find is that in this proprietary data, if you treat cancellations in the regression model, you find that there are fewer passengers allocated to canceled flights, right? And so that's not a passenger choice. I don't choose in advance whether or not I'm going to take a flight that is canceled, otherwise we would find 0. But this is because the airlines, when making cancellation decisions, are actually considering their passengers. So we feel like that's actually kind of a good thing here. And so canceled flights tend to have fewer passengers on them, and then looking at, obviously, the number of seats available on the plane. So we train this all on 1/4 of booking data, the proprietary booking data from a large carrier, and then we generate essentially our choice set. So using the flight information we have, the flight schedules we have, and using the coupon sample, we're able to generate a set of possible itinerary choices that passengers might have taken. Right? What are reasonable connection times? What are reasonable routes? So that's going to give us a large choice set, and from that choice set, we can then apply this multinomial logit model to simulate passenger itineraries. Right? So essentially, we are taking this aggregated flight information and through simulation, disaggregating it down to an individual itinerary level. And that gives us a total number of passengers on direct routes and one-stop proportions. We have to take a little care in how we do this allocation. If you think about this process of simulating passengers to itineraries, it's sensitive to the order, right? We're taking into account how many seats are on an individual flight. So we randomly reorder all of our itineraries so that there's randomness both in terms of the allocation and randomness in terms of the regression model that we've estimated, this logit distribution. And then, again, kind of continuing with the simulation approach, once we have I'll call it realistic because it's my research, a realistic distribution of passenger itineraries. Right? Once we've actually recovered the heterogeneity in the passenger routes, then we use recovery algorithms to see, based on the flight schedules that actually happen, how would we recover those passengers? So passengers who missed connections, what flight had seats that they could have been put on next? Passengers with cancellations similarly. Right? And taking into account the actual constraints based on the seats on the aircraft. And this allows us to essentially recover the delays that passenger would experience. So I mean, in some ways, what we're doing is we're starting with aggregate data. We are disaggregating it by adding passenger heterogeneity, and then we're re-aggregating it to estimate the passenger delays. Right? One just technical note: when we do this, we actually look at a maximum disruption. Not everyone, it turns out that even the aggregated data we have is not a complete sample. So we have to use we have to be careful about how we deal with the recovery. If we waited till everyone could be recovered, it could be multiple days because we're missing some of those flights. So we set a cap, 8 hours for daytime disruptions, 16 hours for evening disruptions. And by doing that, we estimated in 2007 that there were 245 million hours of US domestic passenger delays. So if you assume a cost in 2007 dollars of $37.60 per hour, this was a total cost to passengers of $9.2 billion. And similar to the earlier study, but now across the full set of major carriers, we could estimate that out of all passenger delays, about 52% of passenger delays are due to a delay experienced on their individual flight, 30% due to cancellations and the subsequent reaccommodation, and 18% due to misconnections. As we expect, the passenger delays are significantly larger than the average flight delays. Again, so recovering this heterogeneity allows us to see that the passengers themselves are experiencing more delays than the aircraft. So the 30.2 minutes of average passenger delays compared to an average flight delay of 15.3 minutes. So So that was kind of the first project, and we've decided to take a similar approach, looking at how crew impact flight delays. So it turns out the FAA is very interested in measuring the performance of the system, and they've largely, as I said earlier, looked at flight delays. And so they use existing simulation models for delay propagation through the aircraft, because they don't have information on passenger or crew. But crew schedules create another source, obviously from an operations perspective, of flight delays and cancellations. If there's no pilot available for the plane, we can't fly it, at least not yet, maybe in the future. But right now, if the pilot hits work limits, is not available for a flight, we won't be able to fly the plane. But we don't have publicly available data. So we use a similar, so we're proposing a similar approach. This is work in progress. We've collected proprietary crew scheduling and recovery data to match with the flight delay information across the different types of carriers, network, regional, and point-to-point. And here, instead of looking at a discrete choice model, we're essentially trying to simulate airline operations. So we're simulating how airlines would schedule flights with respect to crew and how they would recover the crew schedules, right? So we're building essentially parameterized operations models for both the crew scheduling and crew recovery, and then the research, where the magic happens, which hasn't happened yet, will be fitting those optimization models against the proprietary data. So how can we best set the parameter values to mimic the airline operations? In particular, one of the things that comes up in crew schedules is, what is your set of choices that you're, for crew recovery, what are the set of paths that you're actually considering? So the more we can make those paths look like the paths that airlines are choosing in practice, the better. And then again, using this sort of re-aggregating the data set once we've considered crew to think about how flight delays are impacted and update the simulation models. But I think that this general approach of starting with aggregate data and using simulation to sort of recover that heterogeneity and then re-aggregate has worked well in my research. So, thank you.
So I'd now like to invite our panelists to come back and sit on the hot seat. So let me briefly, I'll briefly summarize kind of some of the takeaways that I took, but I want to frame it all in terms of one particular question that I'd like to hear some discussion on. So we heard from John Barton in the morning that we're just a few months away from the Back to the Future date, and so we're all thinking about why we don't have the promises there. Now, there weren't that many promises. There was the hoverboard, which is cool. But you know, I think whenever we hear about the future vision of what's possible, and we've been doing that all day, a natural and immediate question we should be asking is, what are the main challenges that we personally see and that we think are bottlenecks that need to be addressed? And so, since this is a session on methodology, I want to ask that question in the context of technology needs and methodological needs. So I'd like to ask our panelists to comment a bit about what they each individually see as some important challenges, because obviously, as we've been hearing all morning, there are policy questions, cost questions. There's a whole slew of challenges that everybody is doing their small part to address. So that's my main question. And just to kind of bring it back, since we've heard about 50 minutes of presentation, what I heard from each of you, if you'll allow me to briefly summarize, Chandra painted a broad picture of the different possibilities and different challenges of heterogeneous data, and in addition, combining computational approaches with knowledge and expertise from social sciences, and you talked about how that's very important. And in particular, you ended with the idea that more uncertainty needs that modeling needs to take that into account. Joydeep gave us kind of an overview of big data through the ages before it was cool to talk about big data, and left us with some thoughts on new tools that have become more popular in the research community, namely matrix and tensor factorization, and told us a bit about the promise of those. Xiaoqing told us about really the promise of video as an extremely rich sensor that can capture quite a bit, but also told us about some of the fundamental challenges latency issues, and this question that fundamentally a lot of computation is required, and so coupled with low latency, perhaps you don't have the time to send it back to the cloud, and we need to think about some intermediate solutions to really realize that. And finally, Doug told us, really, you know, the way I heard your presentation, Doug, is that you focus on the fact that everything here depends on data, but the data that may be available is perhaps not the data that we fundamentally need. And so in particular, aggregated data is what Doug was discussing. So I'd like to turn my question to you and see if you have any comments and your personal thoughts on what are the kind of main challenges that need to be addressed by new technology or new methodology. So I'd like to focus on that because I know there are many policy issues and various other challenges. So we can do it in order, or someone who has some thoughts can.
Go ahead, Doug. You want to start? You want to do the reverse?
Do the reverse, yeah.
The pressure's on, Doug.
Sure, challenge. Well, I mean, I think
you can be narrow or broad. I mean, if you want to tell us about what you're thinking, or or just solve all the problems at once, then that's fine as well.
That's fine. Yeah, I mean, you said not to focus on policy, but I mean, the one issue which I think is somewhat technological and methodological is how to keep data secure, right? That one of the reasons that we don't have proprietary data on passenger and crew is because of the risk, right? I mean, because it's proprietary. There's the competitive risk of that data. And so figuring out ways that we can allow companies to share their data with researchers and the government in a way that they feel comfortable and is fully anonymized, I think is a big challenge. I think we're also at a point where all of the actors see the value in data, but they don't quite know how to monetize it, right? So people hold on to their data with the thought that in the future they will be able to monetize it. And so hopefully, I think that as we learn more about what data can and cannot do, companies will be more open to releasing some of that information, I hope.
Thanks.
Yeah, so actually I wanted to echo part of Doug's concern on data, but maybe point to a different direction to say that this is not just this could not just be solved by policy, but hopefully technology too, in the sense that one of the main challenges we're starting to see or sense is we all know that it's great to aggregate different sensors of data input, and that would give you a holistic view of what's the situations you're monitoring and trying to learn and mining. But typically the ecosystem is set up in such a way that the data may belong, or at least in today, belong to different organizations, and different people sort of deploy their own sensors. So it becomes kind of a gap in how sort of in the data access problem. And the other thing is that the same collection of data you collected from the ground potentially could be of value for different, for different application developers for their own needs. But again, the application developers may not have the right ground of access to the same data. And it's also a legitimate concern, even if, let's say, two different application developers are interested in the same data, the data provider may have their own concerns in sharing that data. The reason why we think it could be resolved from advances in technology is that I believe data science may provide us the right tools in, for instance, querying secure data, or sort of transport, or sort of only providing the right insight to the specific applications without reviewing the fine granularity of the raw data they're interested in. So there may be an opportunity for providing a data mediator role, but who is going to facilitate that role? Maybe a combination of policy and technology will need to come together to make that happen. Thank you.
Thanks.
So I actually feel that the key challenges are really socio-political, business costs, business incentives, policy, and so on. And perhaps that's because I'm on the data side and I can see a lot can be done. But if you also look at the evidence, actually we heard a talk from Google in November, and now their car has driven more than 770,000 miles without an accident caused by the Google car. So that's really remarkable. In my mind, now they're commercial offerings, so couple of weeks back, we got the Tesla Model D as a loaner car, and that has autopilot, so it can follow lanes, traffic signs, increase, decrease your speed, self-park. Mercedes has an option. If the backseat people are doing backseat driving, your front driver's seat can actually swivel, and you can talk to them face to face. So these are now commercial offerings. So I think those things are very possible. Now, to do it at scale, especially in the intermediate setting where some of the infrastructure has all these capabilities, but then you also have old cars. I'm not sure how they can be retrofitted with such technology. Old infrastructure, maybe in dense high-tech cities you could do this, but how about you go into the boonies? How will this work? Those are definitely challenges. But I think from the technological side, there is security issue, of course. But if you think about the Tesla that can be operated remotely, as far as I know, there've not been any there've not been any break-ins yet. Even though conceptually one could just hijack that car and take it wherever you want. So I think even the security, they are, we have to be aware of the issues, but that's not possible.
Thanks. Chandra, you can bring us home.
Yeah, I think each one of us has our own biases in terms of addressing that question. I see the representation of human behavior as an important issue in any of the data analysis work that we do. In terms of transportation in general, we have the infrastructure, we have the technology, and of course we have the users of the system, which are humans. And I have felt that in this large discussion, there's been a lot of focus on technology and infrastructure, but not as much on how humans might adapt and what might be the unintended consequences. I talked about some of them earlier on, but the classic example that comes to mind in the context of technology is airbags. When airbags were installed, yes, there's no question that there's an engineering effect. That is to say that airbags do save lives and reduce injury severity. But what we have also found is an offsetting hypothesis in the sense that humans, as soon as we knew that we had an airbag, we started driving more aggressively. That is a clear indication of how humans might adapt and might change in terms of our behavior. And the same way in terms of crashes. When we look at crashes, it seems strange, but when the conditions are rainy, we find that the occurrence of crashes is much lower, not higher. And that's because, as humans, we understand that there are some risks when it's raining, and we therefore tend to slow down some more. And so there are all of these adaptations of how we might live, how we might change our behavior in owning vehicles. I think that's an interesting and important point in the discussion that we should not lose sight of.
Okay, I think we're just about out of time, so I want to thank all our panelists again, and well, let's do that.